Okay, so can everyone hear me? This probably is fine. Okay, good. So thank Koji for a very nice talk, and I was really hoping one day that Chen will actually tell us the Tsinghua Maths Department and the NCTS are actually the same building. So instead, there was a GPS mishap. I was ended up in the student dormitory. So okay, so and this occasion is very nice, and I think some of the crowds here, well, given the closeness between the Kyoto group and our NTU and also Tsinghua, we see each other on a monthly basis. So this almost feels like a family gathering, and so instead of trying to actually give a very organized talk about the recently published work with one of the former members of Kyoto University, Kono, I'm going to try to use this opportunity to give a kind of progress report. And it's not going to be terribly structured, but it's some of the things that I've been thinking about with a few of my students and a couple of people at the Tokyo University that we are trying to put together, and hopefully the paper will materialize in the next time we meet, probably in a month or so. So, okay, so what's this about? It's about thinking about some unconventional operators in the conformal field theory in general, and also thinking about their connection with the ADS CFD correspondence. So, so part of the talk will be kind of pedagogical and putting some basic background material, so the audience, a lot of students, if any questions, please do not hesitate. Okay, so for your conformal field theory 101, normally what do we start with? Well, we start with a local primary operators, and they should transform as a representation on the conformal symmetry group. And in the case of Euclidean space, so we conformal symmetry group is actually SO1, D plus 1, and the different representation are actually labeled by the cartons on the basically the subgroup of this conformal group. So one of them is non-compact, it's SO1, 1. You can think about this as a two-dimensional Lorentz group, and therefore the corresponding carton is a continuous value, and that's what we normally call the scaling dimension. And on the other hand, we can also label this particular representation on the rotation symmetry group, and this, in this case, the SOD, and the familiar case would be something like symmetric tracelets, or we normally call the spin J representation. Okay. So actually, for this symmetry group, if you learn from your group theory that actually has a wild symmetry group, in fact, it's a much larger wild symmetry group. But now if you consider something like a restricted version, in such a way that what do you do? Well, you basically change your carton quantum number. And we can basically, under this restrict wild symmetry group, I'll define this, well, I already said here, that this is a particular type of wild symmetry group that actually leave the Kashmir eigenvalue carried by those representations invariant, and do not mix the continuous and the discrete label. So the only one left for the SO1, D plus 1 is a Z2 symmetry that which basically take you your scaling dimension to basically D minus the delta, and you also perform a wild reflection on the your SOD symmetry group. Okay, why do I care about this? Well, so there are actually a few caveats here where you can see that normally if we think about the scaling dimension to be positive, and you are looking at, for example, well, a very strongly coupled system, and the scaling dimension will be very large, and this value can actually be negative. So you don't normally think about, well, when you think about local primary operators, you don't think about those negative scaling dimension. But rather, what we are looking at here is a class of a non-local operator, and that's going to be one of the main focus of today's talk. So basically, those two, but in terms of group theory, since they have the same Kashmir eigenvalue, they are actually equivalent representation. So they should be some kind of linear map that related those two different kinds of representation. And this one was actually considered in the beginning of conformal field theory, in the classic paper by Ferrara, Grillo, Parisi, and Gatto, that we can basically introduce such a linear map and kind of formally consider the two-point function which we will obtain from this kind of new type of operator, and perform the following coupling. Okay, you might just view this as some appropriate integration kernel. That which later we're going to see that why this is well motivated. But right now you can think about that this kernel will allow you to generate, once you feed in a local primary operator of a scaling dimension delta, then you will actually have another scaling dimension operator with scaling dimension e minus delta. So if you kind of put them together, you actually get a conformal integral. Okay. So in the simplest case, that we are actually, for example, the rho is actually a symmetric traces representation. Then what we are doing was actually consider something like this object. That O here is the primary operator with a spin J, and you are basically the integration kernel here. Basically, you have this power like x minus 2 to d minus delta, and then you have some indices which take care of the basic contraction in such a way that the left-hand side, since you are not doing anything to your spin indices, then you will actually still get the symmetric tracer representation. But only this scaling dimension here that to ensure if you just come to the power that here have a d minus delta on the top, and bottom you will also have a d minus 2 times d minus delta. So you actually have a d minus delta on the other side. That's a promise.
Yeah.
Yes, go on.
How can you make sure they exist?
I mean, there's no other possibility.
I don't know. It's based on
Let me see.
There's no higher order.
There's no higher order.
Higher order. So in OP, so normally you have a higher order.
Oh, you have descendant, sure. There's no, I mean, but we're looking at the primary order. That's what you're asking about. And also that, yeah, okay, I guess the way to actually answer your question that is, okay, for group series, there's nothing stopping you from having those representations. Yeah, and then the question is really that, how do you actually construct those operators explicitly when you give them to start with, a local one to start with, and to construct a linear map. So in general, I don't think there's any objection for having this linear map. Yeah. Okay, and so we can see that so both of those two operators. So this guy now you can say this is a nonlinear, well, it's a non-local operator that you basically have taken a local guy and smear over your entire space-time. But technically, that both of them actually carry exactly the same quadratic Kashmir value, which is given by the following. So what does it tell us? Or what do we need to care about? Yeah. So the point here is really that when we think about quadratic Kashmir, the first thing we usually think about in the context of a conformal field theory is that we will think about, well, quadratic Kashmir equation and the famous equation derived by Dolan and Osborn basically tell us that this is a second order differential equation, and that allows you to determine what exactly the so-called conformal block, which are the important kinematic building ingredient in conformal field theory, should actually look like. But it boils down to solving some differential equation. Right? And now we are looking actually at some degenerated solution, and the only differences between them is that they will actually exhibit different asymptotic behavior, and you can only pick out, for example, at a small value of this variable d and d bar, which is called the cross ratios. So a lot of things I'm not going to be very well defined. Well, I mean, I'm not going to write it out explicitly on the slides, but any doubt has to. So they exist. Basically, they are allowed solution, just minimally allowed solution. They correspond to allowed solution for the quadratic Kashmir equation. So you wonder, yeah, next question is that whether they should also contribute somehow to your correlation function and so on. So actually this situation, right, this mapping the delta to d minus delta is nothing like new in the concept of ADS-CFT. Right? I mean, on the onset of ADS-CFT, the first thing what do we do? Well, we try to solve the Klein-Gordon equation inside the ADS space. And basically there were two solutions. Right? There's one guy like delta. Well, it basically depends on different behavior approaching the boundary. That one guy basically goes like R to the delta, and the other goes like R to the d minus delta. And we know that depending on one of them will correspond to physical fluctuation, and the other will correspond to like the source term, and will source some primary field carrying the delta being on the boundary CFT. So also, there's another interesting type of this. The integral representation we saw just now, in terms of transformation, also has another very similar analog in the context of more recent development of ADS CFT. This is due to something, this whole gentleman, which I think recently become quite popular. It's called the HKLL formulation or representation of the bulk field in terms of a boundary field. So the key aspect you have to take away here is just that basically when we think about those non-local, well, actually we just try to unpack this equation a little bit now. This is the simplest form for the scalar case. What it says is that the about scalar field propagating in the ADS space can actually be written in terms of basically a local primary operator, but now you actually kind of smear over the entire boundary space. And the kernel here is precisely taking the following form. And what is this? This is precisely about the boundary propagator of an operator as if you carry the scaling dimension d minus delta. And we can see that if we try to take the r go to zero limit, we actually recover a consistent, well, basically we recover the same kind of expression as a shadow transformation if this guy is basically having the following decaying behavior. In other words, carry the source. Okay, so now it's the case for the Lorentzian, for the Euclidean CFT. So now if we actually go to the Lorentzian universe we actually live in. So actually the conformal symmetry group is actually the SO2, D. And now the main difference is in terms of thinking about representation is that there are two copies of a non-compact content subgroup. Now, so how do we think about, well, so basically the subgroup we are looking at is SO1,1 delta and SO1,1J, and then there's a compact rotation symmetry group. So J here now actually can take a continuous value. So roughly the way to think about it is really how we originally going from the when we learn in group theory, that starting with a compact rotation group and then going to the non-compact guy. So you started with, for example, a representation of SO D, and you basically only continue to the Lorentzian signature, and the J here, roughly speaking, you can think about it as the number of the boxes in your Young diagram for SO D. Can just count it in the first row. Okay, so but the biggest difference between the SO2, D and also S1, D plus 1 is actually that the kind of similar restricted wild symmetry group is actually now the DA, the dihedral group, is 8 different elements. So those interesting elements can actually be generated by the two following transformations, acting on basically those content labels, labeling and representation. So the first one, which I denoted SJ, or later I'm going to refer this as the spin shadow transformation, that basically leave the scaling dimension invariant, but actually instead acting on the kind of J, I would just call it J rather than call it spin, that in such a way that into this combination. And later we'll see why this is also a well-motivated change. And also the other guy is actually called a light ray transformation, or explicitly define how those linear map, like explicit linear map actually look like. But right now you can just view this as, okay, so I have those, I have all this Kazan label, and I have a corresponding quadratic Kashmir eigenvalue, which can go by one slide. And those transformations basically leave the quadratic Kashmir eigenvalue there. Fine. So how many possibilities there are? That's the question. So, and so this, the other guy, is the light ray transformation. In this one, it's kind of interesting. We actually exchanged both the spin, both the J and delta. while leaving the representation under the so D minus 2 invariant. So you can count the order of the transformation. Each of those two would do twice to going back. But if you combine them, so yeah, you have to do it 4 times to come back to your original representation. So this allows you to generate 8 different possible representation. And why are those 8 guys are also interesting? Well, so basically now they represent this basically telling you that when you are trying to solve for the quadratic Cashmere equation or trying to find the conformal block in the Lorentzian conformal field series, there's actually a kind of A4 degeneracy. That there's such a degeneracy that actually only going to get lifted when you look at the asymptotic value. And why do we care about those? Well, honestly, it was because you might have heard recently about this Lorentzian inversion formula, which basically tells you that how to actually project it out given the correlation, 4-point correlation function in the Lorentzian conformal field series, how to actually extract the corresponding basically scaling dimension OPE coefficient, basically by thinking about those conformal blocks as something orthogonal basis. But the orthogonal basis here need to be existing in basically written. You have to consider all the different possibilities to actually have a sensible answer. So that's one of the reasons. But those things are actually, initially they seem quite rather exotic. But I think after there was a nice work by Chen and Stuffing, but also there's a very nice another piece of work by Schomers and the collaborator that they also realized this kind of A4 degeneracy group is actually also related to the wild symmetry group of something called BC2. Well, is related to BC2 group, and what the underlying integrable system which underlie this related to this quadratic Cashmere equation is precisely a BC2 collegial cell selection system. So that's another direction which we are interested in talking about. So another work we are working on with another Kyoto member, Junichi Sakamoto, which hopefully we can report next workshop. So okay, but anyway, so what's the corresponding linear map for all this transformation? Well, the first one I'm just writing down as a kind of taking the weak rotation from Euclidean to Lorentzian for completeness. This is the shadow transformation in the Lorentzian signature. And the second one is more interesting. That's the spin shadow guy, which corresponds to the SJ just now. So in order to implement this transformation, so the way you should really think about it now is that, well, so now we have SO 1,1 delta and SO 1,1 J, and basically they are both continuous values. So we should actually somehow treat those two quantum numbers on equal footing. And we should also introduce basically another continuous kind of coordinate which allow you to implement this transformation. And this coordinate is something known about, we call this a polarization vector, or Z here. And so now if we, so that's why I'm writing those two in parallel. That first you think about the shadow transformation here. This was basically inserting, if you just focus on the simple scalar case, that you basically implement this kind of like complementary pieces. And for the spin shadow, you do the same. You treat this polarization vector as a continuous label, continuous coordinate, and insert it something like a propagator. The polarization vector enjoy the property of a z² equal to 0. It's a light line. So, so basically, this combination you can also view this as a d minus d prime to the power 2 minus d minus j. And the reason why, so j here basically is the scaling dimension. It's the same in kind of equal footing with the scaling dimension here. And the reason why you only have d minus 2 coordinate here is simply because when you think about the integration measure in well, basically you are on the line in the d dimension. So this is basically completely parallel with a discrete spin case that where you for those people who know a bit more about those things, that you have those polarization vectors which you contract with the integer indices. And now if you basically treat this all this we call an embedding polynomial for those tensor field as a kind of two-variable polynomial with appropriate two-variable function, more precisely, with appropriate scaling. So this allows us to treat them on a complete equal footing. And the final one is this lie rate operator, which also become popular when people are thinking about usually the popular one here is putting the energy momentum tensor here spin over the line direction. So that's how we can realize this. And so the natural, so this is what I was kind of mentioning earlier, that one of the main reasons we really want to care about those is that those different kind of operators also contribute to the exchange between the two, OP exchange between the two scalar primary operator, and they exhibit very, very type of different asymptotic behavior. To be more precise, that the conformal block we normally want it when the cross ratio are very, very small, which would behave in the following form, multiplied by some hypergeometry function or keep this ratio to be fixed. And on the other hand, those additional operators actually have a different asymptotic behavior that they can actually go like the following. So for the case of integer spin J, we can use the hypergeometry identity to show they are equal, but when they are, J is actually a continuous value, then they take a very different value. So we should really try to, there are few directions we should really be thinking about is that, yeah, okay, let me do more concrete about one thing. Sorry, those are just the background. So the point is that, okay, this is one slide I just mentioned, like what Kilnison did and I did. That so when we consider integer spin, all right. So we basically previously the result was always saying, okay, for general d-dimension Euclidean signature, so we can only have an integer spin. That the closed form for conformal block is not really known, and you only know for even dimension, you can actually write a hypergeometry function. But what we did was we realized that, in fact, we also know this conformal block have this Mailing representation. And when you actually perform the integration and pick out all the codes, there are infinite number of them, but those infinite summation can actually be summed over into basically this Appel's hypergeometry function F4. And there are various kind of parameters which you define here. They are not very important, but the only important message here is that we can actually write down the d-dimensional, general d-dimensional conformal block with arbitrary spin exchange in terms of finite summation. So this summation here actually consists of 5 different variables, but it's mathematical. It's a nice way, it's a mathematical can actually execute this summation together through the numerical calculation. Okay, so, and also in our paper, we consider a continuous generalization of spin J. So basically, we also follow the strategy of thinking about the Mailing representation. And in order to construct those Mailing representation, what we really did, it was we would have to do is think about, we construct the conformal block by contracting two different copy of 3-point functions. So in order to generalize this contraction for the integer spin case, and we basically also have to employ this integration over the polarization vector and with this complementary spin. So basically, this choice, another way to actually view this type of choice of spin, the J minus here is actually, I didn't say that, but it's D minus 2 minus J, is such a way that this integral, okay, this integral when you view in the Z variable, is also a conformal integral in the basically D minus 2 dimension. And so they can basically employ a lot of previous known technology to perform the conformal integral in D dimension to actually obtain the following the result. And this was basically the key modification when we were trying to basically generalize our representation for Mailing representation from integer to the continuous case. So, and the important thing here is that we have to actually also separate the J and the shadow, the J bar dependence. because actually each of those pieces later on will actually generate a very different asymptotic behavior. And this is just exactly the same analogy that when you think about how you construct the conformal, if you follow basically what Dolan and Osborne did before, that if you consider constructing the conformal partial way by performing this contraction on 3-point function, what you ended up is not just one single conformal block, but actually the delta and its shadow. So there are two copies here, and we are basically realizing these things exactly in the spin, basically in the kind of spin variable, if you want. But now they are completely equal. Okay. So we also have a closed form, and we use a Maillard representation, and we have some complicated result, and you can look at our paper. So that's probably I mentioned some of those in the talk before, or even Hideki might have mentioned this. But, okay, so let me, how much time? Okay, I will try to accelerate a bit before I run. 25 minutes. Okay, before I run too much. Okay, I'll just show some equations first. And so those are, basically we know the answer. That's all we want to say. So, okay, this is our difference. But what I really want to get to here is that, okay, so about holography. Right, so this is another something I've been playing with for the past few years. So, okay, so just some recap. So for the integer spin J, right, now we want to cook up, so what's the goal here? We want to cook up a holographic dual of those conformal blocks. And for the integer spin J cases, the holographic dual was actually known as a geodesic Witten diagram. And those are the two pictures here, and this was done by Hijano and per crowds and other crowds in the UCLA group. So I just draw a cartoon here, and let me briefly explain that. So this is not a conventional Witten diagram people usually use to calculate. But the only difference is here is that we replace the, so this is since I'm looking at 4-point function to begin with. So this is a 4-point exchange Witten diagram. And what we are doing is that we cut the bound-to-bound propagator right in the middle and into two boundary. And the reason you can do that is because we know how to do the harmonic analysis in the ADS space, and basically the boundary propagator allow you, when you do a appropriate integration measure, allow you to express the harmonic function in the ADS space in terms of those kind of on-shell type of object. But what it differed from the normal Witten diagram was that instead of, like when we do the Witten diagram, normally we will try to integrate over the exchange vertices over the entire ADS space. Well, this is one possibility you can do that which preserve the entire ADS isometry, and it should because of the conformal symmetry. But another possibility here is actually that you can actually also restrict those interaction vertices to move along the geodesic, which also preserves the ADS isometry, hence the name of geodesic Witten diagram, and those geodesics basically come from the connecting the boundary point, which we insert a different pair. Well, you basically have to pick two different pairs, and that corresponds to the CFT. You take a different exchange channel that they connect to this. So we can basically further, well, using this kind of split representation, we can further kind of unpack this diagram a little bit and just focus on what I did with Chen and my former student Henry Gore about this 3-point geodesic Witten diagram, that which basically consists of basically a 3-point vertex, and we slightly modify this, and we only allow the interaction point to move along the geodesic of two of the external guy, which I call the O1, OP1 and OP2. Because they are kind of useful, because this actually leads us to another kind of object that I'll be talking about later, the OP. So, okay, first, what does those 3-point geodesic Witten diagram correspond to? Well, they can only correspond to one thing, and they can only correspond to the 3-point CFT correlation function, because just from the tensor structure, we know that, what I'm trying to say is that they can only differ from the 3-point CFT correlator up to overall coefficient. because this case we are looking at the scalar tensor. So you actually set up in the previous slide the two scalar and this is a tensor field. The tensor structure is uniquely determined in this case. So and we know this it's determined by the conformal symmetry and the isometry in the ADS, and whatever the vertices you get here, right? This a different. This delta here is the ADS covariant derivative, and K here is basically, so I'm working with this embedding space formalism which I probably in some of the code can mention before, or that I'm quite popular nowadays, maybe all the details I can't talk today. So the K here basically give you the contraction of the with the polarization vector. So but in any case, when you after you do the computation, each of those are the boundary propagation for that diagram. But now the biggest difference here is that we are restricting the interaction point X you're integrating over, only moving along the geodesic. So if you perform a calculation, and what you really see is that you get the following computation. So the Pij here is really how you write the separation of the two different points in the embedded space. And then when you project it back to the physical space, then you get the x1 minus x2 squared and so on. So, but this the point is that this guy is really it's basically the 3-point scalar tensor function. And so that's what I'm trying to say here, that any other vertices will feel exactly the same tensor structure. And this basically encoded, you can also try to encode all the result in the following kind of master integral, which you can also rewrite it in terms of the appropriate differential operator made out of this symmetric tensor acting on just a scalar guy. So this is just one simplification one can perform here in that calculating state. Okay, so why do I mention this? So this is one of the objects that we are trying to explore. So something called OP block, but that's in the different literature. So we are one of the agenda we are trying to do by working with Tazuma, with expert in the complex entanglement entropy, is that there seems to be some literature that exists on the other side that they're talking about these things called OP block. And basically the project started out when we were chatting with each other over some conference on the way to India. So right, so basically this seems to be recently getting quite popular in computing those entanglement and entropy business, which I know very little about. Now, but what they call OP block is this, in the simplest form, is actually just some bilocal operator. I guess this was defined by Chen and his friends. That it's basically just a fancy way to package what the possible product OP, including all the descendants that what you was asking just now, into this thing they call it B, and they call it the OP block. And it has the benefit that, for example, that if you consider like taking two of those guys together, then you get a conformal block, etc. But the thing is that this has OP should that is actually uniquely fixed by the conformal symmetry. So to get an explicit form of this guy, then what we can do in the Euclidean space, that we can actually basically consider something like projector construct of those shadow operator which we introduced earlier, and basically treat those things. Well, these are some of the points. Yeah. So once we introduce a projector, we are actually treating some of those guys as a Bragg cat in a sense of quantum mechanics. And take a contraction that we can rewrite the explicit form of the OP block into the following. It's basically that you are trying to integrate over some 3-point function, and but now instead of looking at the scalar tensor with the scalar dimension delta, but now you are actually looking at the 3-point function scalar, but with its shadow dimension, and integrate over this operator you originally want to. This is a particular OP block you want to associate. So this is a local operator. This is non-local. But just playing those equations explicitly, because the point is that now we actually know what the 3-point function is explicitly, right? So if you plug in the equation and try to rewrite them a little bit, so you realize that from the basic Feynman reparametrization, that you can actually re-express those combinations in the denominator in the 3-point function into the following. But what do you notice? Aha, first thing you notice is here is that, well, so this combination is precisely what we had before. This x lambda. X lambda is the geodesic. That if you reinterpret this integration variable lambda as a line parameter of the geodesic, that then what you notice that this x lambda is precisely describing the geodesic connecting the boundary point. So what you see here is almost exactly the same. Yeah, almost similar. I mean, it's not quite identical yet. So you can rewrite this combination in the following form. And we can now actually focus on it and try to interpret this as a holographic configuration. So it's actually very natural that just when you think about this, one of the reasons they were introducing this guy was also trying to think about entanglement in the context of areas. Maybe some of the people working on this case and so on. Yeah. So anyway, so first thing is that for the case of a scalar j equal to 0, so the statement here we covered here was that we can actually rewrite this OP block in terms of two of those boundary propagator, and the multiply was known as the HKLL field. Right? This was the one I introduced earlier in terms of boundary construction. That so the statement, the clean statement we are making here, or basically this was one of the main statements that people were making. The holographic deal of this OP block, both in the Euclidean and Lorentzian signature, actually correspond to essentially drag this HKLL field along the geodesic. But this is, I mean, they make a quite big deal out of it, but I mean, maybe I'm not doing a very good justice on this. So, but it's really just dropping out very naturally from the property of those integrals. So, and furthermore, we can actually try to generalize this kind of statement to an arbitrary speed that also almost for free from the expression previously. So what we noticed was that this combination V012, which was really the tensor structure with d of the mass. What we see is that it's actually, it can be precisely along the geodesic. That's the point. Precisely along the geodesic. We can actually rewrite it as a combination of this geodesic line, its derivative, and contract it with this antisymmetric tensor. And so if we now actually regard this following combination, which satisfies the property that is orthogonal to a boundary point and is also line, and that's precisely a polarization vector which you can have for a boundary tensor field as a possible boundary polarization vector since it works, then what you see is that you can rewrite this integrand, which over the boundary point P0 into well, there's some contraction with this derivative. But now you act on this, but then the dz act on d basically, then contract with z0, just do a swapping. So this actually leads us to a very nice, very simple generalization of holographic view of Euclidean spinning OP block. So the structure is basically the same. That you are dragging this spinning generalization of the HKLL field directly along this geodesics. So, well, in other words, what we are looking at is very good. Yeah, we are basically looking at this type of diagram. Okay, and now we actually now introduce this kind of HKLL field. So it's basically precisely corresponds to this thing. So in other words, the holographic deal of the OP block is basically what we have in terms of the 3-point geodesic within the diagram. And also, from this kind of simple, very simple analysis, we see that this representation of HKLL in terms of basically this almost like a scalar boundary propagator contracted with this field, this is a boundary spinning field. Is exactly consistent with all the earlier results by the Kabbalah, Lipschitz, and students operator for those. So that was for Euclidean case. The more interesting case was for the Lorentzian case. So the natural modification you have for Lorentzian, of course, you have to care about the causality. And so what you have to restrict it is to integrate the entire space-time. You have to integrate over the causal diamond where the x1 and x2 are acting as the two different tips. And so there's an essential modification what you can do, right? In order to impose a causality, then you can divide it into different cases of whether things are space-like or time-like separated and insert the appropriate step function to impose a causality, make sure things cut out in the right way, and just recycle the Euclidean case. But that seems to be rather, well, the whole construction seems to be rather broad. You have to try different things for different cases. So instead, we are trying to work in the momentum space. So, and that would make this whole discussion about causality a lot more transparent, and that's what we are kind of tidying out in the paper right now. So more precisely, what do? We basically only Fourier transform one of the guys. We only Fourier transform the Pythagorean exchange. And so now we can also introduce this momentum space projector that basically this guy is a kind of vacuum exchange. And then you also have all the other the pairing between the momentum space, the primary operator and its shadow, and you impose some delta function. So dV is the total operator for tensor contraction. So this was also nothing new. Actually, for beginning students, this was actually this was actually in the very nice 1970 lecture notebook by Mac and his collaborator. It contains a lot of reading that book really teaches a lot of useful things. Tonight, probably be laughing about some of the things that I do. So for the case of x12 being space-like, we can actually rewrite using this projector. We can rewrite this Lorentzian OP block into the following form that where the Q here is basically coming from considering the Fourier transform or really Fourier transform. One of them of the Whiteman function. And on the other hand, if you want to generate all the spin structure, and that's part I really have to give those people in the 70s that really working on the corresponding differential operator that would generate those spin, and it turns out all these different Jacobi functions. So those derivatives is kind of rather complicated. Like you have to actually expand it in terms of the Jacobi for the use appropriate coefficient and act on term by terms. So the first preliminary result we got was that so for scalar case, for consistency, you should really be able to generalize the picture of the Euclidean one we had earlier. And indeed, that was the case. And how do we do it? Well, so first things we noticed that there's a modified Bessel function identity. So there was a modified Bessel function which I didn't mention earlier, but it's that we can actually change the. I can never remember there's the first type and second type, all of the other. We can actually relate them, and plus I've changed a variable to rewrite in the case of scalar into the following form. And what we noticed was that so here. First, in those U integration, we can also do a change of variable to recover the geodesic integration for the external leg we had earlier. And what's really nice here is that this guy was actually also known before by HKLL that this precisely corresponds to the momentum space representation of the field. And so as a consistency check, that we can also perform the we want to recover the original guy in the physical space to do an inverse Fourier transform. There are those nice identities that which allow you to recast the Bessel function back to the original form. And this is exactly what we were expecting before. This is just, well, now we are working in the physical space that this is the HKL field we had before, and there is the appropriate causality imposed, and also additional external geodesic. So this is one of the results we have. Okay, and I think that's basically why well, there are some of the equations which is too complicated to show on the slide now. But right now we have a few directions we are going. So let me just say it out loud. We are obviously finishing the case for spinning case, and there are some issue with the gauge choice between the conserved and non-conserved tensor field, which we are trying to tidy up. And then we are also trying to work out the case for the light case. And the reason why this is useful is that to reconnect. Yeah, so we're trying to put things together. Trying to reconnect with the non-local operator we had earlier was that now given this kind of HKL type of representation, okay, so now we can actually have, well, originally we were thinking about how to impose all these kind of nonlinear transformation, which allow, well, the linear transformation, which allow you to obtain those non-local operator in the ADS side. But probably the better way, I mean, that's what we are also tidying up right now, is that the better way to really do it is actually think about those bulk fields in terms of this HKL representation, then directly apply those transformation in the boundary CFT in this boundary field we have introduced in this HKL representation, and then you basically obtain the bulk field, their corresponding holographic field, and we have checked this a few of those cases to recover indeed the boundary propagator, which we are hoping to get for those non-local operator, and also the vertices and the Witten diagram and so on. So those things we hope to tidy out. Yeah, we'll try to talk about the information about steps. Okay, let me end here.
I do this point, but here in the first part you explain that.
Yes.
If we have a shadow transformation, which is a solution of bulk, the ADS bulk equation, there are two modes here.
Yes.
I want to know what the Lorentz.
Good, very good. So the way to really think about this is following. So, okay, so basically the quadratic catchment operator in the CFT side can be directly mapped to the Klein-Golden, well, if you also encode the speed for the massive case in the ADS side. So the two equations are basically equivalent. You are solving for one guy for quadratic catchment, and you can actually it corresponds to solving the Klein-Golden problem, or basically all this for the free field propagation in the ADS. And you can even show that in fact that's one of the earlier check for the geodesic Witten diagram as a holographic field for the conformal block. We showed explicitly that the integral that we constructed using the Witten's rule and pointed out. This guy really satisfies the equation, equation of motion governing the propagation of this field, but this always operating in between.
So may I understand that is 8, so you have the 8.
Yes, so good. So in the case of Lorentzian case, now you have to ask the question now, what are the holographic field? And they are basically also allow solution inside the ADS, well, inside the ADS space, but now with a different asymptotic behavior.
So all of those are
right. And so one of the goal, I should have hammered this harder, but basically that one of the goal was really trying to control what are the holographic field of those Lorentzian conformal blocks. Okay, so there are a few obstacles you have to overcome step by step. First is that you have to think about what are the corresponding boundary propagator. I mean, we actually know the final form already. In fact, we also know implicitly how to actually, what are the right propagator you have to had before. But it's how to systematically generate them, right? Now, for those non-local operators. But also, what I'm trying to say, yeah. So also, what are the possible interaction vertices? Right. I mean, that's somehow how to construct, because now you don't have the discrete spin. Usually, when we construct a vertex, right, we have a discrete spin, then you just write down whatever contraction you have to have a symmetry in there and so on. But now you don't. Basically, now all these things replaced by obviously integration. Beta integration replace your tensor construction and so on. So you want to ask, okay, what are the possible vertices you can have for those? And because different vertices, they sometimes equivalent of the equation of motion as well. Right, so when you do a appropriate motion, just dropping off the motion. So those are the issues we were trying to answer. Okay. So it turns out it was probably more systematic to go one step back, to instead of thinking about four-point function, to start with this kind of option. And that's basically this is what the direction I was thinking about. And Tatsuma was thinking about the OPE block. And but this guy also has a very natural connection with OPE block, as I was trying to explain in the second half of the talk. And it turns out everything kind of reduces down to this HKLL representation, which we first have to generalize, then we get the OP block spinning free, and then now we are thinking about how to act on all these are results still for local continuous, but discrete speed, but we are trying to apply those integral maps to the non-local guy. So, but I think the is sorry, I'm not being very structured, but I was making a disclaimer in the beginning. This was a thing that I tried to get it right. I think it's okay.
Okay, let's make a video.